Welcome, class. This first section of video notes is actually going to be an algebra review to hit all of the things you hopefully remember from previous courses, rather than actually jumping right into our pre-calculus material. The first thing I wanted to go over for you guys is the different classifications we have for groups of numbers. For example, the largest group of numbers is actually something we call the complex numbers. And within the complex numbers, you have the real numbers that you guys are probably most familiar with working with, which is numbers like 7, even decimals like 8.23 repeating, and some of our weird symbols like pi, which are infinite decimals. So those are the real numbers because they do not have an imaginary part. So out of the a plus bi part, the b is a 0, so this part is ignored. However, if you look at having a is 0 instead from a plus bi, then the real part is missing, and all you have left is the imaginary part of the number. That's why we call them the imaginary numbers. And these either have an I in them, or you'll see the square root of a negative value, which is what we define I as, the square root of -1. So whenever there's a negative inside of the radical, it's an imaginary number. We definitely spend more time working with the real numbers, and even within the real number sets, you'll sometimes hear terms like the rational numbers, which are any numbers that can be written as a fraction. And this can be misleading to people, because even numbers like 0.5, even though that does not appear to be a fraction, you could think of that as 1/2. So that decimal could be written as a fraction. In fact, most things can be written as a fraction. The exceptions are the irrational numbers, which include the infinite non-repeating decimals. So when I say non-repeating, I mean 8.23, since we drew that bar over it to indicate that it repeats forever, that would actually count as a rational number. There is a way to write it as a fraction. But a non-repeating decimal would be something like pi. The digits are different forever. You can't just say it keeps repeating the 0.14 pattern over and over and over again. So the most common examples of irrational numbers are non-perfect squares. So square root of 2, square root of 3, square root of 5, or our weird symbols like pi and e, which we'll look at more later on in this class. Now, within the rational numbers, which has all those ugly fractions and decimals, as well as whole numbers like 3/1, we have a group called the integers, which does not include the numbers in between 0 and 1, or 1 and 2, or 2 and 3. It just includes those nice, full, rounded off numbers, not the decimals and fractions in between. And if you're including both the negative and the positive versions, we call them integers. If you're only including the positive versions and 0, we call them the whole numbers. So most of your counting and everything, those are all done with the sets of integers or whole numbers. Now let's talk about how you would express having multiple numbers or multiple answers to a certain problem. When you only have several numbers to express and you aren't interested in all of the fractions and decimals between them, then we use the curly brackets, which look like this. They are often sometimes called the braces, to list out specific values. For example, if I wanted to say what all the even numbers are between 5 and 13, then I have 6, 8, 10, and 12. By putting them inside of these braces, we're indicating that we only care about these 4 specific numbers, not any of the values in between or anything to that effect. So if you have several set answers, don't forget to use the curly brackets or braces, and then just separate them off with commas. Now, what happens more frequently in this class is you will often need to express a whole range of numbers. You will care about the fractions and decimals in between numbers. So first is our inequality version of saying all of the numbers bigger than 3, which would mean numbers like 4, 5, and 6. But by not putting a line underneath the inequality symbol, I'm saying 3 is not an answer to whatever I have. On the number line, this can be either represented with parentheses, or sometimes you might see them use an open circle instead, and then still have the line to indicate all of the numbers not including 3, but bigger than 3. So that's another way of doing this. However, in this class, probably most commonly, you will be seeing something called the interval notation, which is the one you see represented here in the middle. Whenever you see a pair of numbers, either in parentheses or in brackets in some combination, separated with a comma between the two values, the number on the left is the smallest number you're talking about for your set, and the number on the right is the biggest number you're including in your set. So for example, here, you can see my smallest number is 2, and I'm including all the x values bigger than that until I hit 5. I don't want any x numbers bigger than 5. So for interval notation, I just put 2, 5. The next important detail about interval notation is whether you use parentheses or brackets. Just like with inequalities, when you are not including the endpoint, so not including 3 in this case, that's when you use parentheses for that value. So this is specified that 3 is not an answer for interval notation. Whenever you see a bracket, that means you are including that endpoint. So for this inequality that said all of the numbers less than or equal to -1, I need to use a bracket to indicate that -1 is a possible answer. Now you'll notice that the infinity symbols will always have parentheses. That's a rule, and it's important for you guys to know. You should add it into your notes. You always use parentheses for the infinity symbols, whether it's the positive infinity, which means going up forever, or negative infinity, which means going down forever. Never put a bracket on those. So in this example, we had all of the x values bigger than or equal to 2, so I put a bracket on the 2 for the smallest number in the set. And then I wanted to go all the way up until I hit 5, so the number on the right-hand side is 5, but I don't want to include 5, so parentheses for it. And again, there is another way of drawing this with the number line. You could instead use a filled-in circle whenever you're including that endpoint, and then this line would extend over. Since it's not including 5, that one would be an open circle. So this is another way of representing the number line if you're ever asked to draw one. This slide I will go through quickly because I hope you guys are comfortable with adding, subtracting, multiplying, and dividing negative numbers. Basically, the short way of representing multiplying two numbers together is if they have the same sign, then the answer is positive. If you're multiplying two numbers and one's positive and the other is negative, so they have different signs, then your answer will be negative. And also, as a quick reminder, double negatives cancel out. So if you ever have minus a negative, that's the same as adding. If you ever have adding a negative, that's the same as subtracting. So you can always clean up your equations a little bit by taking two plus and minus signs that are right next to each other and simplifying them with just one symbol according to these rules. The most important thing I really wanted to stress is the exponent rule. Please, please, please be very mindful of the difference between -3 in parentheses squared, which actually equals 9, because this is saying -3 times -3, so positive 9. And this case, where I don't have parentheses, which is saying -3 squared. This is actually only squaring 3 and then putting a negative in front of it. So the answer to that one is -9. And that's why I have this symbol here to indicate that these two answers are not equal to each other. You have to be careful about this, especially when plugging numbers into your calculator, whether you should be using parentheses around the base of the exponent or whether you do not need parentheses around it. They are different answers, and it will give you, you will get points off if you're careless about that. Looking at fractions, don't forget that when you are multiplying two fractions, you multiply the top and the denominator, the numerator and the denominators, separately, and you don't have to have a common denominator for these operations. So it doesn't matter if the numbers on the bottom match or not. You just multiply straight across. So 1 times 3 is 3, 2 times 5 is 10. For division, most of you guys learned this as keep, change, flip. The process of what you're actually doing is you're flipping the second fraction upside down, which we call the reciprocal. So instead of dividing by 3/5, you can think of this as 1/2 times 5/3. So keep the first fraction the same, change the symbol to multiplication, flip the second fraction, and then follow the above operation of going straight across. 1 times 5, 2 times 3. See if you can simplify, but you can't in this case. This is just another way of writing the exact same question, 1/2 divided by 3/5. Fractions are division questions. They're the same thing. So what you can do instead is keep the first fraction the same, 1/2. Instead of dividing, call it multiplication, and take the reciprocal of whatever you're dividing by. So the reciprocal of 3/5 is 5/3, and then multiply straight across. Adding and subtracting is a little bit trickier and a little bit more work intensive because you do have to have a common denominator for these, either adding or subtracting. And then the other thing that's tricky is you only actually add the numerators. Do not do anything else to the denominator. Once you get the same denominator for both fractions, you only add across the top. So in this example, I've shown you that for the fraction on the left, I want to turn 2 into a 10, so I'm multiplying both the top number and the bottom number by 5. So 5 times 1 is 5, 5 times 2 is 10. For the fraction on the right, I need to get this 5 turned into a 10, and I do that by multiplying 2. So I have to do that on top, and I have to do that on bottom. So I end up with 2 times 2 is 4, and 5 times 2 is 10. Now we have the exact same fractions. 5 over 10 is the same as 1/2, it's just in a different form. But now I can take those two fractions and I can add the numerators since I have a common denominator of 10. So now 5 plus 4 is 9. Bottom stays the same. Please don't add those numbers in the bottom. No, do not perform the operation in the denominators of a fraction. For simplifying, when you just have a fraction like 6 over 4, I think you guys know how to reduce those pretty well. It gets a little bit trickier when you have lots of different variables and factors in there. So the process is basically that you want to factor everything out as much as possible. So break them down into little prime numbers. 45, for example, can be broken down, if you remember the simplifying radicals process, making like a factor tree out of this. It's the same as 9 times 5. And 9 is the same as 3 times 3. And once you get all of the numbers broken down into prime numbers, you can just write them out, multiply together. So 3 times 3 times 5, that's what I wrote here. And x cubed is the same as x times x times x. Then I did the same thing in the bottom. 15 can be broken down as 5 times 3, and then those are both prime numbers, so you can stop there. So you can see I wrote 3 times 5, and x squared is x times x. So once you have everything in the numerator and denominator as factored down as possible, you can go through and cancel out any of the matching pairs in the numerator and denominator. So I had an x on top, x on bottom, cancels. Same thing there. 5 on top, 5 on bottom, 3 on top, 3 on bottom. Once you've canceled out everything that you have in common in the top and bottom of the fractions, look at what's left. In this case, I have a 3 and an x on top, and I don't have anything left on the bottom, but let me stress that this does not mean that you have left a 0 behind. When you are canceling these things out, you're actually leaving behind a 1, because what I'm saying is 3 divided by 3 is 1, 5 divided by 5 is 1, x divided by x is 1, x divided by x is 1. So when I say I'm canceling things, I'm actually just turning them into 1s, which means I have 3x over 1 left as an answer. But that's unnecessary writing something over 1, so I would rather have you just leave your answer as the 3x. And I will always expect you to simplify fractions. That's the little comment I have here. Don't even bother asking if you have to reduce or simplify your fractions. The answer to that is always yes. You should never leave a fraction outside of a simplified form.